Welcome back to the classroom. Today we're going to be covering one of the additional sample papers supplied by NESA. This is for Module 5, Question 14. So if we go through this question, it is on centripetal force circular motion. We have a toy car placed facing towards a rotating turnable table, as you can see here. The car was held in place by a force sensor connected to the center of the turnable table. The center of the mass of the car was 0.5 meters. Okay, so that's our sort of radius of our circular motion from the center of the turnable table. The reading from the force sensor was recorded at various speeds of rotation. A stopwatch was used to time the rotation of the turnable table. The linear velocity was calculated from the period of rotation. The graph shows the force on the car versus the square of the linear velocity of the car. So that's our information here with the graph. As you can see, linear velocity square, and also on our vertical axis, force. Okay, so that's what we have here. So looking at the chart, it says use the graph to determine the mass of the car. So what we're dealing with here is obviously if we have uniform circular motion. The reason why we know it's uniform circular motion is because the radius stays consistent. The velocity is changing, but that is irrelevant to that. So we are dealing with circular motion. So when it comes to circular motion, there has to be some kind of centripetal force causing this car to have this circular motion, and so we can use the following formula. Fc equals to mv squared over r. Okay, so there's a couple of things we can work out. We know that r is a constant. Okay, so r is 0.25 meters. What we can then do is actually use the line of best fit. Okay, so this line all the way along here, the line of best fit to substitute into this equation. So we have force over velocity squared, that is our gradient. Okay, so if I was to firstly find the gradient value, then we can also talk about how we can find mass from this part here. So we have this point here, which is 1, 2, so 2, 0. And then over here we have points 28 and 3.5. Okay, so according to our gradient value, so Fc over v squared is equal to 3.5 subtracted by 0 divided by our horizontal components, which is 28 minus 2. So let's find the value for that. Okay, so the answer I get is 0.1346153.846. That's a ratio between the force and v squared. We don't really need to have units because that's just our gradient value that we have here at the moment. You could round this off to 3 sig figs for your calculation because it's not specified in the New South Wales syllabus how many sig figs to use, but let's just use the total value first. Okay. All right. Next, let's try and find mass because that's what we're trying to do. So if we actually look at the equation we had, it was Fc divided by v squared, and that gives us the equation m over r. Okay. Which means if we rearrange this equation, which we'll do in a different color, so people can sort of see where the arrangement goes, we need to move R over to this side. So the way we do it is we times both sides by the radius, v squared equals to m. So whatever value we had here for fc over v squared, we times that by the radius, which is 0.25, and let's see what answer we get here. Okay, so the answer I get is 0.0338615 kilograms. Could round it off to 3 sig figs if I wanted to. 0.0337 kilograms. That's how you do this part here. The mass of our car is 0.0337 kilograms. Okay, so continue on to the next page. And we go to question B here. In this one, it says, identify possible errors in the data and outline how to reduce their effects on the estimation of the mass of the car. So in order to answer this question, let's go back to the actual stimulus and the actual questions themselves. Okay? And we'll try and work it out using the information provided. Okay, so when it comes to errors, just a reminder, there are two types. We have systematic, and we also have random errors. All right, so I want you to sort of think about what's happening with our data using these two types of error points. So systematic is the way we measure things. If let's say if our force sensor wasn't correctly calibrated or zeroed properly, so let's say our force sensor actually when we first started measuring was 0.1 newtons off. What could we do there if we keep measuring it like so? So that's what we have with systematic errors. If we have a non-zeroed measurement and we carry it out for all our measurements, then that's what we refer to as systematic error. The next one we have is random errors. In this case, that just essentially means that we haven't controlled our variables. So what could affect the way we control our variables? If you actually have a look here, we're using a stopwatch. So we're actually depending on our reaction time when it comes to measuring for the exact time it takes for one rotation for this car to go in one full circle rotation. So that can obviously mean that our reaction time can stop at various points. It might not stop consistently at the same point every time. So those are the two errors we have: systematic from the sensor, random error because of the way we use the stopwatch. We need to then think about how we could mitigate these kind of errors as we go through. Okay, so let's come back to this question here. So our first error, we can say, we can talk about our systematic error. So systematic errors from the use of the force sensor which has not been zeroed or calibrated before measuring. Okay, so that is one of our errors. So how do we fix this? So to reduce the effect, the force sensor must be zeroed before usage. And you know, there are probably some occasions where systematic errors, you know, the actual decimal point of the measurement of the force, you can't get rid of it or you can't zero it properly. Then if that was the case, then obviously subtract that away from your final result. Okay, so if this is not possible, ensure to subtract the non-zeroed value from the final measurements. Okay, so that's how we deal with that one. Next one we want to talk about is our random error. So with our random error here, that would be, like we said, with the stopwatch. So the random error can occur through the use of the stopwatch, which is subjected to the reaction time of the recorder, hence the time of rotation could vary. Okay, so that could be the case. So there's a couple of ways you could minimize this error. One is by increasing repetition. So you could do multiple recordings for that specific rotation. So if you're moving so if you detect a certain force on the sensor, you could try and record the time it takes for one revolution multiple times and then do an average. Or what you could do is to allow it to spin, maybe say 10 times. That's just an arbitrary number. Allow it to spin 10 times and then, using the time you have, average that to give you the time for one rotation. So that is also another way to minimize the potential error of those rotations, because you have a larger sample size. Okay, so there's two methods. So go with the one we talked about just then. So to minimize error, allow the table to rotate 10 times, recording the time taken. Divide this value by 10 to obtain an average time of the 10 rotations. This will provide a better approximation of the period of rotation and thus the linear speed of the car. So that's what we have there. Obviously, if we want to calculate the linear speed, let's also make sure that the table is rotating at a constant angular velocity. So for this to work, ensure omega, which is angular velocity, is constant. Okay, and so that's what we get. Additional point that I just want to highlight that you don't necessarily need to take in, but it might be useful information, is remember the relationship between linear and angular velocity is v equals to r times omega. So if I were to work out what the angular velocity is, because it's constant, and also what the the radius is, so angular velocity I can work out from the rotation, then I can work out linear velocity. So that's kind of the relationship we're trying to show for here. So let me just kind of move out of this screen here, or just enlarge it again so you see the full answer, full response. Okay, so what we actually said was, what were the errors of this experiment? Systematic errors is the sensor not being collaborated or zeroed properly. Now we can just fix that by zeroing it before using it, or we can essentially subtract that non-zeroed value from our final measurements and then go on with our plotting of the graph. The random error that we will go through is most likely using our stopwatch, which is subject to the reaction time of the recorder. So the time of rotations might not be very consistent. So to minimize this, we can just increase the number of rotations and record the total time, and then divide that as an average rotation time for ourselves. And then that gives us a better approximation. And if we know what the angular velocity is, or we can keep it constant, we can then work out the linear velocity. So that's how you answer these questions regarding circular motion. Hopefully that gives you a better understanding of how to approach these kind of questions related to circular motion, and also the difference between systematic and random errors. Thank you for listening, and I'll see you next time.